Good afternoon and welcome to this presentation on topic Uncertainty in Measurement. This work was done in the frame of the Erasmus Plus project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. This tutorial is prepared by Professor Vladimir Dimchev from University Saints Cyril and Methodius in Skopje, Faculty of Electrical Engineering and IT, Macedonia. What is measurement uncertainty? The word uncertainty generally means doubt. In the context of measurement uncertainty refers to the doubt about the validity of a measurement result. In other words, no measurement is perfectly exact, and uncertainty reflects the range within which the true value is believed to lie. The term uncertainty on its own can refer to both the general concept and to the quantitative expressions used to describe it. When a particular measure is meant, additional descriptors or qualifiers are used. This concept is standardized in international guidelines, such as the PEMS-JCGM 100:2008, known as the Guide to the Expression of Uncertainty in Measurement. The formal definition of uncertainty in measurement is as follows: it is a parameter, associated with the result of a measurement, that characterizes the dispersion of the values that could reasonably be attributed to the measurand. This parameter may be expressed, for example, as a standard deviation, a multiple of it, or as the half-width of an interval with a stated level of confidence. But why is uncertainty in measurement important? Uncertainty quantifies the reliability of a measurement and is essential for accurate decision-making and valid comparisons. For instance, in calibration, the uncertainty must be reported in the calibration certificate. In testing, uncertainty can determine whether a test result passes or fails. Thus, understanding and reporting measurement uncertainty is fundamental to ensuring the credibility and usefulness of measurement results. In every measurement process, 5 key actors play a role. First, the measurand, which is the quantity to be measured, such as temperature, pressure, or length. Second, the instrument or device, which is used to perform the measurement. Third, the standard, which provides a reference for the measured quantity and ensures traceability. Fourth, the method, which defines the procedure or technique by which the measurement is carried out. And finally, the operator, whose knowledge and skills can directly influence the reliability of the result. Together, these 5 actors determine the accuracy, precision, and overall quality of a measurement. Accuracy versus precision. Accuracy, or how close a measurement is to the true value. Accuracy refers to the closeness of a measured value to a true or known value. Precision, or repeatability of measurement. Precision refers to the closeness of 2 or more measurements to each other. This slide shows 4 cases. The first case is when accuracy and precision are okay, the second case is when precision is okay but accuracy is not okay. The third case is the opposite, accuracy is okay but precision is not okay, and the fourth case is when both accuracy and precision are not okay. 2. Sources of measurement uncertainty. Errors, random and systematic. In general, a measurement has imperfections that give rise to an error in the measurement result. Traditionally, an error is viewed as having 2 components: a random and a systematic component. Note, error is an idealized concept and errors cannot be known exactly. Random error is generally attributed to unpredictable or stochastic temporal and spatial fluctuations in influencing factors. These fluctuations, often referred to as random effects, result in variability among repeated observations of the same measurand. Although it is not possible to eliminate random error from a measurement result, its impact can typically be mitigated by increasing the number of measurements. Random errors are characterized by their tendency to oscillate unpredictably around the true value. Note, the experimental standard deviation of the arithmetic mean, or average, of a series of observations should not be conflated with the random error of the mean, despite its occasional designation as such in the literature. Rather, it represents a measure of the uncertainty in the arithmetic mean attributable to random effects. The precise magnitude of the error in the mean arising from these effects cannot be determined. Would you like me to make it even more formal? closer to a scientific publication style, e.g., with references to metrology standards such as UKIM, Guide to the Expression of Uncertainty in Measurement. Systematic error, similar to random error, cannot be completely eliminated, although it can often be reduced. When a systematic error results from a recognized influence quantity affecting the measurement outcome, it may be quantified. If the magnitude of this error is significant relative to the required measurement accuracy, an appropriate correction factor can be applied to compensate for its effect. After correction, it is generally assumed that the expected value of the error arising from the systematic effect is zero. Unlike random errors, systematic errors consistently bias results in a particular direction. The measurement error is often denoted as the absolute error, delta, defined as difference between measurement result and so-called true value of measurand. However, the concept of a unique, true value, is no longer considered valid in contemporary metrology and is not supported by relevant international standards, e.g., UKIM. In practice, the result of a measurement is regarded as an estimate or approximation of the measurand, and it is meaningful only when accompanied by an associated statement of measurement uncertainty. In most cases, the best available estimate of the measurand is expressed as the arithmetic mean, average, of a series of measurement results. The uncertainty associated with a measurement result reflects the incomplete knowledge of the true value of the measurand. Even after applying corrections for recognized systematic effects, the measurement result remains only an estimate of the measurand's value. This is due to the combined influence of random errors and the imperfect correction of systematic errors. Note, a corrected measurement result may, in fact, be very close to the actual value of the measurand, and thus have a negligible error, even in cases where the reported uncertainty is large. Consequently, measurement uncertainty must not be confused with the unknown residual error. In practice, numerous factors can contribute to uncertainty in measurement. Among the most significant are an incomplete or ambiguous definition of the measurand, imperfect realization of the measurand as defined, non-representative sampling, wherein the sample under investigation does not adequately reflect the defined measurand, insufficient knowledge regarding the influence of environmental conditions on the measurement, or inadequate measurement of such conditions, personal bias in the interpretation of analog instruments, etc. These sources of uncertainty are not necessarily independent. Indeed, several of those listed in points A through I may collectively contribute to an additional source, denoted as J. Furthermore, it should be emphasized that unrecognized systematic effects cannot be explicitly accounted for in the evaluation of measurement uncertainty. Nevertheless, such effects invariably contribute to the overall error of the measurement result. Type A and Type B evaluation of uncertainty. According to the Guide to the Expression of Uncertainty in Measurement, UKIM, the evaluation of measurement uncertainty is generally classified into two categories, depending on the method of assessment: Type A evaluation, and Type B evaluation. A Type A evaluation of uncertainty is based on the statistical analysis of a series of repeated observations. This approach utilizes methods of statistical inference, such as the calculation of experimental variances and standard deviations, to quantify the uncertainty component. A Type B evaluation of uncertainty is carried out using information obtained by means other than repeated observations. Such information may include calibration certificates, manufacturer specifications, reference data from handbooks, results of previous measurements, or scientific judgment based on all relevant knowledge of the measurand and the measurement process. It is sometimes suggested that Type A evaluations correspond to random errors, while Type B evaluations correspond to systematic errors. However, this interpretation is misleading and not adopted in the UKIM. The distinction between Type A and Type B evaluations refers exclusively to the method of evaluation and not to the nature of the error. Indeed, components traditionally regarded as systematic can, in certain circumstances, be evaluated by a Type A approach, and conversely, effects often regarded as random may be evaluated by a Type B approach. Note: The classification of uncertainty components into Type A and Type B is therefore methodological and does not imply a direct or exclusive link with random or systematic errors. The Type A evaluation of standard uncertainty * is applied when several independent measurements have been made for one of the input quantities, under the same conditions. Assume that the repeatedly measured input quantity Xi is the quantity Q. If someone make n greater than 1, statistically independent measurements, the estimate of the quantity Q is arithmetic mean value or average, of the individual measured values Qj, equation 1. An estimate of the variance is experimental variance S, Q, of values Qj is given by equation 2. The positive square root is experimental standard deviation. The best estimate of the variance of the arithmetic mean is the experimental variance of the mean equation tree. Because the positive square root is experimental standard deviation of the mean. Now, the standard uncertainty associated with the average is the experimental standard deviation of the mean is given with equation 4. The foundation of Type A measurement uncertainty is rooted in statistical analysis, with its origins traceable to the seminal contributions of de Moivre, 1733, Gauss, 1809, and Laplace, 1812. The figure presents a histogram based on 20 repeated observations of the temperature. To employ the tools of mathematical statistics, it is necessary to transition from the discrete representation of measurement results like on the figure, to a continuous function. This continuous representation is expressed through a probability density function, which provides the mathematical framework for analyzing the distribution of observed values. If the number of measurements n is progressively increased while the width of the observation interval is simultaneously reduced, a limiting case is approached in which n goes to infinity and the interval delta t approach 0. In this limit, the discrete frequency distribution of the observations converges to a continuous representation. This representation is expressed as the probability density function p, t, which characterizes the distribution of measurement outcomes in a mathematically rigorous manner, see figure. In the evaluation of Type A measurement uncertainty, the choice of probability distribution depends primarily on the number of available measurement results. When the dataset is large, the Gaussian, normal, distribution is typically employed, as it provides an accurate model for the statistical behavior of repeated measurements. Conversely, when the number of observations is small, commonly fewer than 10, the student's t-distribution is preferred, since it accounts for the additional variability introduced by estimating the population variance from limited data. As the number of measurements increases, the t-distribution gradually converges toward the Gaussian distribution. For sample sizes on the order of 200 or more, the two distributions are practically indistinguishable. Both the Gaussian and the student's t-distributions are continuous probability density functions defined over the interval -infinity to +infinity. They are symmetric about their central value, and their maxima coincide with the arithmetic mean of the measurement results. This symmetry ensures that deviations above and below the mean are equally probable, reflecting the fundamental assumption of random errors in repeated measurements. When working with the Gaussian distribution, we can solve three important types of problems. First, we can calculate the probability that corresponds to a specific interval of values. Second, we can determine which interval of values corresponds to a known probability. And third, we can estimate how many measurements, or data points, are expected to fall within a given interval. These applications make the Gaussian distribution one of the most powerful tools in measurement science and statistics, because it allows us to quantify uncertainty and predict outcomes with confidence. Type B. The Type B evaluation of standard uncertainty refers to the assessment of the standard uncertainty associated with an estimate 11 of an input quantity Xi, obtained by means other than the statistical analysis of repeated measurements. In this approach, the standard uncertainty U, x, is determined through scientific judgment and the systematic use of all available information regarding the variability Xi. Sources of such information may include results from previous measurement data, established experience regarding the properties and performance of instruments or relevant materials, manufacturer specifications and technical documentation. Calibration reports and other certification data. Published reference data, including values and uncertainties provided in authoritative handbooks. The Type B evaluation thus complements the Type A approach by incorporating prior knowledge, expert judgment, and documentary evidence into the uncertainty assessment, thereby ensuring that all relevant sources of variability are taken into account. In general, Type B measurement uncertainty is characterized by assigning an appropriate probability distribution function to the input quantity, based on available knowledge rather than repeated measurements. These distributions are typically selected according to their geometric form, reflecting the assumed likelihood of values within a specified interval. The most commonly employed models are the rectangular, trapezoidal, triangular, and U-shaped distributions. An example is shown in the figure, where a rectangular distribution is illustrated. If the bounds of the distribution are denoted as a plus and a minus, the width of the interval is given by 2a. Under this assumption, the corresponding standard uncertainty is determined according to the following expression, 5. Triangular distribution is used when values near the center of the interval are more likely than those at the edges, forming a triangular probability density function. In this case, for interval width 2a, the standard uncertainty is equation 6. Trapezoidal distribution represents a case where there is a central plateau of equally likely values, with decreasing probability toward the edges. If the central plateau has width 2b and the full interval has width 2a, the standard uncertainty is equation 7. Now is one example. A manufacturer's specifications for a digital voltmeter state. Between 1 and 2 years after the instrument is calibrated, its accuracy on the 1V range is 14 times 10⁻⁶ times the reading plus 2 times 10⁻⁶ times the range. Consider that the instrument is calibrated on 1V range. For Type A evaluation for an independent repeated measurements, arithmetic mean is 0.92857 volts. And standard uncertainty Type A is 12 microvolts. Type B evaluation is obtained from the manufacturer specifications. If symmetric rectangular distribution is applied, then half width of delta V is 15 microvolts. For standard uncertainty Type B is obtained 8.7 microvolts. The combined standard uncertainty of this estimate by combining Type A and Type B standard uncertainty gives value of 14.8 microvolts. 3. Calculation of the combined standard uncertainty for uncorrelated input quantities. For a set of uncorrelated input quantities x1, x2, x3, and so on, the combined standard uncertainty UC of y of the estimate y is given with equation 8. Where function f is represented with n independent variables. Delta f cross delta xi is partial derivative of the function f with respect to xi. And uxi is standard uncertainty for each xi evaluated by Type A and Type B evaluation. For example, DC power is measured according to the expression power is equal to voltage multiplied by current P equals U multiply I, with 2 Fluke 45 multimeters, one measuring voltage and the other current. Also the specifications of the instruments are known. The following values are measured, equals 8.0125 volts, measurement range 10 volts. equals 50.105 milliamps, measurement range 100 milliamps. Measured DC power is P equals 0.40147 watts. To find the combined uncertainty, the uncertainty of voltage and current which are directly measured values must be determined. In this case we use Type B evaluation with rectangular distribution from instrument specifications. In this slide we have two tables for voltage and current which are given by manufacturer of multimeters. From specification for 10 voltage range, see yellow box, in first table for half width is obtained 0.0022 volts. Now, uncertainty of voltage for rectangular distribution is 0.00127 millivolts. From spec for 100 milliamps range, see yellow box, in second table for half width is obtained 0.045 milliamps. Uncertainty of current for rectangular distribution is 0.026 milliamps. Since voltage and current are measured by two instruments, their values can be taken as uncorrelated. Sensitivity coefficients, partial derivatives of power for voltage and current, are del P/del U equals I and del P/del I equals U. Now, for the combined uncertainty of measured DC power is obtained 2.1810 on -4 watts or 0.218 milliwatts. 4. Expanded uncertainty and reporting. Within the framework of the European Cooperation for Accreditation of Laboratories, EAL, it has been established that calibration laboratories are required to report the expanded uncertainty of measurement U. This parameter is obtained by multiplying the standard uncertainty UC of Y, associated with the estimate Y, by a coverage factor K, equation 9. When the measurand can reasonably be assumed to follow a Gaussian, normal, probability distribution, and the evaluation of the standard uncertainty is deemed sufficiently reliable, a coverage factor of K equal 2 is prescribed. Under these conditions, the reported expanded uncertainty corresponds to a coverage probability of approximately 95%, thereby providing a high level of confidence in the stated measurement result. Example: calibration and calculation of uncertainty for 10 kΩ standard resistor with direct method. Calibration is done with digital multimeter HP3458A with 8½ digits with direct connection of resistor to DMM. Ambient temperature is 23 ± 2 degrees Celsius. The temperature coefficient of the resistor according to the manufacturer's specifications is 5 ppm/degree Celsius between 18 and 28 degrees Celsius. The total resistance measurement uncertainty can be expressed with following formula. R equals R DMM plus delta R DMM plus delta R RES plus delta T. Where R DMM is digital multimeter, DMM, reading. Delta R DMM is DMM measurement uncertainty. Delta R RES is resolution limit of the DMM. And delta RT is effect of resistor temperature coefficient. DMM uncertainty. From the specification of digital multimeter follows, 10 ppm plus 0.5 ppm of range. For a 10 kilo ohm resistor, that is 10.5 ppm equals 105 milliohms. Now standard uncertainty for rectangular distribution is U equal 105 milliohms divided by square root of 3 is 61 milliohms. Resolution. At 10 kilo ohms, the resolution is 1 milliohm, which is least significant digit. The interval is plus, minus 0.5 milliohms. And standard uncertainty is U equals 0.5 m omega divided by square root of 3 is almost equal to 0.3 milliohms. Temperature coefficient. Assume temperature variation, plus or minus 2 degrees Celsius. Temperature coefficient is 5 ppm on 1 degree Celsius. 10 ppm for 10 kΩ resistor is 100 milliohms. And standard uncertainty is U equals 100 m omega divided by square root of 3 is almost equal to 58 milliohms. The uncertainty analysis for a measurement, usually called the uncertainty budget of the measurement, should include a list of all sources of uncertainty together with the associated standard uncertainties of measurement and the methods of evaluating them, like the table on the slide for the case of uncorrelated input quantities. In this table all quantities should be referenced by a physical symbol xi or a short identifier. For each of them at least the estimate xi, the associated standard uncertainty of measurement u, xi, the sensitivity coefficient Ci and the different uncertainty contributions Ui, y, should be specified. The dimension of each of the quantities should also be stated with the numerical values given in the table. In our table, first row represents n measurements of 10 kΩ standard resistor, the obtained estimate is 9.99993 kΩ, and standard uncertainty is 3 milliohms with normal probability distribution uncertainty contribution is 3 milliohms. The second raw is digital multimeter uncertainty for rectangular distribution, which is 61 milliohms. The third raw is uncertainty from DMM resolution again for rectangular distribution, which is 0.3 milliohms. The fourth raw is uncertainty contribution from resistor temperature coefficient effect 58 milliohms. In this case, for uncorrelated input quantities the sensitivity coefficient is 1. The combined standard uncertainty for measurements of 10 kΩ standard resistor, according equation 8, is 84 milliohms. Expanded uncertainty with coverage factor 2 for probability of 95% is 0.17 ohms. This slide provides additional references related to the topic. Thank you for listening. More information about the project see. Webpage, https://sites.google.com/view/PEMS-ML-Erasmus/about?0. LinkedIn, Erasmus PMS-ML. Email, erasmuspemsml@gmail.com.